King, we just got to Calc 2. What is this Mclaruin series I've been hearing about?
McDonald in math. Yum.
Hello?
Sigma.
Shut up.
I said McLaurin, not McDonald.
What is class for the GPX?
A Mclaruin series is a sum of polynomials, or called a power series, that typically approximates a transcendental function centered at zero. Values near zero increase approximation accuracy as the number of terms increase. Each new term is called the remainder or error term. These terms increase the approximation accuracy.
What that mean?
Real series is an infinite sum of something, and a transcendental function is a function that cannot be algebraically expressed. Did he put?
What do you mean by algebraically expressed?
Kumilionetti froze songing-wu, Tachuko hito expression inawedu serait converten like en expression of power of xampness en constant multiplication monster.
Yes, in other words, transcendental functions are functions that cannot be expressed with a finite combination of multiplication, division, addition, and subtraction of polynomial terms with rational coefficients.
What you mean by center?
Centered at zero means the approximation will start at zero. And as the approximation gets more and more accurate, values further away, both greater or less than zero, will get more accurate too. But remember that I said an approximation near zero, meaning the approximation will only work for values near zero, and the approximation must be 100% accurate at zero. It will increase its approximation accuracy further from zero until a point 2 distant from its center, meaning this approximation will not guarantee an accurate approximation past a certain point away from zero, despite having many terms in its sequence.
What are Mclaruin series used for?
In math, it can be used to solve differential equations and approximate non-elementary integrals. In a more practical sense, it is used in a more optimal way in calculators to approximate values of a transcendental function. This is because calculators and computers can only calculate numbers using algebraic operations like minus, plus, multiplication, and division. So what I'm going to do is show a visualization on how the Mclaruin series works. I'm going to start with a graph of the approximation of ETX and show how adding more terms will converge to ETX centered at zero. Okay, so we got the simple graph of e to the x right here in blue, right here. And we got our Mclaruin approximation of zero terms for now in the purple. And our error graph of e of x is in green, which the equation for this is the difference between the function e to the x minus the Mclaruin approximation. And looking at the error graph e of x, if the error graph is equal to zero at some point, that means there is 100% accuracy between the Mclaruin approximation and our function. We are approximating at the center at zero. And this error graph is telling us by how much is there error. As in, at x equals 0, ETX is greater than our approximation by 1. Our first step is to find an equation that resembles this error graph centered at 0, or close to 0. And we must find this equation and add it to our Mclaruin series to improve its approximation accuracy.
Why must we find that equation?
So we have an equation that gets rid of error.
No, did he put? How to add an approximation of the error to the actual approximation you overput?
Very good question. Brilliant, in fact. That's the million-dollar question. The reason why we attempt to find the graph that looks like the error is that the graph of ETX transforms into a vector from the error Okay, that was a very good question. A brilliant question. Million-dollar question. Now, what I'm about to say is going to be important, and you're going to have to pay attention. You want to pay attention to specifically this part of the video.
People battling just different.
So you may know what is basically the whole point of this video, and if you don't pay attention, you probably won't understand the rest of the video. So, before we get any equation, let's get with the idea that we're adding terms. Why are we adding an equation that looks like the error graph to our Mclaruin series so we can get a better approximation? And the reasoning behind this is, if we look at the error graph and we pick any spot, let's say right here, this error graph is telling me that ETX is 1.5 greater than our approximation right now, at 0.412. That means that in order for this Mclaruin series, this purple line, to get more accurate, as in get closer to the value of 1.5 at 0.4112, we need to find an equation such that at 0.412, it will increase our graph right here to 1.5. Or at least, we're skipping a couple steps here, but that's the general idea. Since it's centered at 0, it should be most obvious that the Mclaruin series should be 100% accurate at 0. So, we need to find an equation, we need to add an equation to make this line at least accurate to the function at 0, which is 1. And we can do that by adding 1, or maybe add a different equation.
but just by adding 1 doesn't account for how it's gonna need to be a better approximation near 0 on this area. Now our starting approximation is 0, and well 0, we know this is not a really good approximation, so what should we add to our Mclaurin series so our approximation has a better accuracy through error? What must we add that looks like this error graph so that this Mclaurin series can look much more like ETX? That is also polynomial, of course.
Euler graph looks like here. Just like mango and block.
It look better as 1.
Ja,
Sigma, the answer should be 1 plus x because of linear approximation.
No, we need to start from the very beginning.
Yes, Kyle, at 0 terms where m of x is 0, it wouldn't be obvious to think that the first term is 1, but it is. There's multiple reasons, but first, m of x equals f of x, where is it centered at? The Mclaurin series is centered at 0, so m of x first term should be 1, in order for the error at 0 for e of x to be 0. The Kwong cube is not wrong either. If you zoom into the graph of f of x at x equals 0, you can see a straight linear line x. So it is not wrong to assume that x is a good approximation, but using x as its first term would not be a good approximation near 0. The general shape is right, but the literal approximation values are not. But what is also true is that the first 1 to 2 terms of the Mclaurin series are going to be the tangent line of a function. This is no coincidence. So, this is what I mean. Let's start with 1. X equals 1, alright? It doesn't look like a good approximation, and this line doesn't look any better than y equals 0 other than the fact that it's accurate at only 1 point, which makes it 99.9999999% error instead of 100%. Actually, rather, don't know about that, but regardless, you get the point. So let's talk about what I was talking about earlier with mapping this Mclaurin series purple line to this blue line, the function etx. In order to do that, we need to add what looks like the error functions to the purple function. Look at where y equals 1, right? For both the error graph and the purple graph, at 0.7, it is equal to 1. Now, if we look at etx, this blue line, we see at the same x equals 0.7, etx is around 2. That's why the error graph is 1 right now. Likewise, if we look at, say, 0.5, negative 0.5, the error graph tells us there is an error of negative 0.4. This negative means our Mclaurin series is an over-approximation.
At that point,
It's at 1, at negative 0.5, etx is at around 0.6. So it's greater than etx right now, but over here, it was actually less than etx. And our goal with adding more terms with the Mclaurin series is to map this approximation to these values that is distant away from etx right now. Currently, it's at 1, at 0.7. We need, at x equals 0.7, to be closer to 2, or at least closer to what the function of etx is at that same point. And this logic goes for every point near 0. We want the values to be mapped. We want the purple function to be mapped onto this function etx. How we're going to do that is by copying this error graph, the shape of it or how it looks, because it tells us the pattern at which the differences is at. We want an equation where it is near, at 0.7, it's near 1, but more closer and closer we get to 0, we want this line that looks like etx, because obviously this is not a polynomial line. We need a polynomial equation that near 0 matches exactly with this function, this error function. So when we add it, this over-approximation right here, this over-approximation goes lower because it's adding a negative number. So when we add this term, it'll go down. But at the same time, since this term is positive on this side, it'll actually, this side, where right here, will go up. It'll be mapped up on positive side, it'll be mapped down on the negative side because of the equation that we use that looks like the error graph. Now, if you zoom in, this error graph looks like y equals x. It starts from the origin. For small values, it does seem like it is at a constant rate until as you go on, it has error of its own. So adding y equals x to the straight line at y equals 1. Let's see. At these points that are practically equal to each other with the error, this purple line will be mapped plus however this much is at this same point, which is 0.1. We add by 0.1 at this point. At 0.3, it'll be increased by 0.3. So, not right here. This purple line will be around right here. 0.5 would be around 0.5. So, we add by 0.5, which is right here. And as you can see, the approximation is closer than what was originally here with this straight line. But it's not exactly etx. And we're not trying to get exactly to etx. We're trying to get close to etx as much as possible. And for this negative side, same logic.
somewhat like this. See how this new red line that added the term y equals x looks more closer to the function than it did with the purple line right here. That is essentially what we're doing when we add by error. We get a line that looks like the error graph, so it matches the pattern at which the error graph increases or decreases, and when we add it to our approximation, we get the line that gets closer and closer to ETX, because we're adding by the error that needs to be equal to ETX. I am Matt Kwong. I am Kyle. I am Simon. Alright, now let's add our x term, and look at that. It does indeed look like a parabola. This error graph does look like a parabola. Let's try doing y equals x squared, and let's especially zoom in to see how accurate it is to our error function. Now, x squared may fit the shape pretty well, but I think we can do better with widening our parabola. We learned in pre-calculus that coefficients less than 1 widen the graph, whilst coefficients greater than 1 narrow it down. So in this case, let's try some coefficients that are fractions. Let's go up to 1/3, as any more would probably be too wide. Let's see. I'm going to copy this. This is 1/2, this is 1/3. Change the color. Okay. So let's turn off the approximation we have now. And this graph, this green graph, is our approximation we have. And the rest are approximations of this graph.
I am now voicing over. While zoomed out and looking slowly near the right side, we can see that y equals x squared is the best pick. If we look on the left side, we now think that y equals x squared over 3 is the best pick. But remember, we are doing approximations near 0, and although these approximations, especially 1/3, is a good approximation, there's technically a correct coefficient to use. Even though it's just an approximation, approximations aren't ever going to be 100% accurate. We can use 1/3, but there is the correct coefficient of 1/2, and to prove that it is technically 1/2, if we look near 0, we said that it's abundantly clear how much closer it is compared to the other functions. But zooming out, since the difference between x squared over 2 versus x squared over 3 versus x squared are so small, they are literally in the thousands in difference. As long as it's near 0, there's no big difference between picking either coefficients. I'll show you in the last problem that we'll do what happens when we don't use the quote-unquote correct term. Look at how the graph changed. Look how the approximation changed too, from 1 to 2 to 3 terms.
Oh, this one looked like x cube.
It looks like y equals 0.
Indeed, near 0 it does look like y equals 0, but y equals x cubed is a better choice. Adding 0 will do nothing for us. So now we're going to pick a coefficient, and for this one there will be a lot of choices.
It would seem that 1/4 or 1/5 are the best pick. Especially here, you can see 1/5 is so close to the error as it approaches 0. But 1/4 in general seems closer. What do you think, Nick?
It looked like hamburger. What about you, Kyle?
You can't pick a coefficient, you freaking giddy blood. Your hires, are you seeing the truth? Maybe if you were smarter kids, you would look towards 0.
Gee, this Kwong guy is scary.
The only person that's scary is Pat God at 3 a.m.
I know he needs a 5-course meal at 3 a.m.
Believing you do at 3 a.m. is pee the bed because your Pat God is calling you solely sigmas arise.
Anyways, yes, we must check towards 0 to see which coefficient to use. As we approach 0, it seems like 1/6 gets closer to e of x. The purple line is 1/6, although it did look like at first that 1/5 seemed like the best pick. So with this, we will pick 1/6, even though the coefficient, especially near 1/6, are good approximations, but for the sake of being right, we will use 1/6. Look at how the Mclaurin series seems more accurate now. I hope you have realized the coefficient and fractional denominator have been getting greater and greater. Instead of individually finding them, I'll use a slider to visually show the possible coefficient values. The graph looks like x to the 4th.
Look like x to 4.
T-Yard, at 900. The left side of the graph, more accurate compared. Point but right CD, more accurate for attention. Tapement it must be un bit.
I don't know, Kyle. Out of all the numbers between 1 and 100, they all seem viable until around 40.
Remember, guys, we have to look at the 0.
Even if we do, there's still so many numbers to look through.
I will spare you from looking for the actual coefficient. It could have visually been any one of them, but the correct one is 1/24. This may not look like the best graph when zoomed out, but as I've said before, if you zoomed in, especially near 0, you'll see that 1/24 has the closest line to the error graph near 0. Spamming random stuff. But remember, even if we didn't pick 1/24 and, for example, picked 1/23 or 1/25, those approximations are good enough near 0. But visually speaking, there is no real reason why to be nitpicky about which coefficient to use. We are going to now add the error term and look at how much more accurate our approximation got. The entire arc looks pretty much like ETX from -1 to 1. If you zoom in there, is still a difference, but very insignificant. If we turn on the error graph, you will see that the interval from x equals -1 to 1, the graph is basically at 0 for the entire region. If you have noticed or may not know, I don't know what you have known or learned when watching this video, there is an actual pattern to the Mclaurin series. This pattern that we have right now is correspondent to e to the x. So although I said approximations are just that, so being So being nitpicky on coefficients is pointless. There is still technically a correct coefficient. This is because if we're trying to approximate a function, we should also be able to approximate its derivative and antiderivative with the same amount of precision and accuracy. When the power rule is performed on these series, the result should be equal to the Maclaurin series of the derivative slash antiderivative of the function. If we weren't picky and got the derivative slash antiderivative, then that's where the problems and inconsistencies will occur. These theories must follow a general rule in order for the Maclaurin series to function as needed, and by extension the derivative and antiderivative. This is a bit out of the scope of this video, but I will just want to show you the growth of the Maclaurin series. So as you can see, the growth is fastest near 0, and when we go further from 0, especially shown on the left side, we see that it takes a lot more terms to even reach to x equals negative 40. Although it seems like my computer is lagging, the growth at which the approximation tries to get more accurate further from 0 does actually take more terms and take much longer for it to get further from 0, compared to when it was near 0, of course.
Okay, so now you guys will do your own problem. Do cosine of x.
I think we start with y equals 1.
Non bro, hit négatif 10e squared.
I get it now. I understand it now. The first two terms are the tangent line, right? So the first term should be 1. But it seems the slope of the tangent line at 0 for preceding x is 0. Next term must be 1.
Nage bro HT, il faut combine un nombre négatif 10e squared de première vertique le match.
Let's not skip steps and do it with the error instead of guessing.
No.
Let's start with 1 and then could do the rest.
The error looked like cosine x moved downward.
Boy.
Pack God please. Humble.
When I zoom in, it looked like y equals 0.
Min premier temps qui use main to far. Zoom to Eric does look like négatif 10e squared like premier set. Gros premier temps, you négatif 10e squared match like love.
You never mentioned the 1/2, but okay, boy.
Which one to pick, guys? I know it's somewhere near 20 and 30. But I don't know which to pick.
Remember, Ming, it doesn't matter. Just pick a good enough one, yeah.
No, if you zoom in it is clear you see 1/24 is the best pick. And I remember double derivative of cosine x is negative cosine x. So that means if I take double derivative of this approximation, the x to the 4th term should have the same coefficient as x squared is right now, but negative. And since x squared coefficient is negative 1/2, the coefficient is 1/2, and that matches. So I use 1/24.
Guys, I got a question. If this was a way to approximate a graph back in ancient times, how did the people find out the Maclaurin series for functions that are transcendental? This way of finding the series makes no sense. If you already have the graph of the transcendental function, why are we approximating?
You're mistaken. This is just a visualization to make intuitional sense of the Maclaurin series, but this is not how the people found or created the Maclaurin series. We're showing you why it works, not how they found it. The series was found before they even graphed these transcendental functions. To look at a series won't tell you anything. People and computers use it to get an approximation of these transcendental functions where we generally don't know the values of. This method is closest to an idea to how your own calculator calculates values of transcendental functions.
Okay, they'll research that a bit.
GPT.
Anyways, I think we'll stop here. If you look right now, the approximation is quite good up until 1.5 on both sides. Right now, I'll show you the series of cosine x real quick. If we look at the series of cosine x and by extension sine of x, they are special in the way that they can extend far away from 0 with a small number of terms compared to the other functions like e to the x. You can discuss why this happens with your class. They don't have much of a problem extending outwards from 0 as much as any other function does with a Maclaurin series. Our last equation is natural log of 1 plus x. The reason why we don't do natural log of x is you can't center natural log of x to 0 because there's asymmetry there. So we use plus 1. Okay, so this should be easy. We've done this 2 times already, so yeah. Since the graph of e of x looks like y equals x at 0, zoomed in and passed through the origin, we do not need a y equals 1 for this case. So we can just start off with y equals x. As you can see, the y equals x looks really accurate to the error function. Yes, it is also a tangent line at 0. Now, for the second term. This graph looks like negative x squared, but slightly rotated. But if you just zoom in just close enough at 0, you can barely sense that it was rotated. In fact, it just looks like negative x squared. So let's try a couple of coefficients. I believe that there is only 3 that, looking at this from afar and close up, it is clear that negative x squared over 2 is the best fit, and it's no contest. So we are going to have negative x squared over 2. And let's look at the approximation now. Now that's way better than any linear approximation, for sure. Anyways, now we are, and now this obviously, the next error term looks like x cubed, especially when you zoom in. So let's look at x cubed. So around right here, it looks like x to the 4th is really accurate. No contest there. But then we looked at the left side and it looks like 1/2 is really accurate. And if we're being honest, picking either or would not really matter. But the actual correct coefficient would actually be 1/3, as you can see, zooming in way closer to 0. 1/3 simply just beats the rest of the coefficients by accuracy. So we're going to add x cubed 1/3 next. See the function now? Yeah, it's getting pretty accurate. Alright, sorry, from the 4th term now, I'm going to show you what I meant earlier in the video about showing you why the coefficients don't necessarily matter. So starting from this one, I'll show you 2 different coefficients and we'll compare them at the end when we get 5 total terms. Compare the 2 graphs to show you that they're really insignificant, near 0, the differences between them when you pick the coefficients. Alright, so this clearly looks like x to the 4th. So let's try that. We're going to try up to 4, and same thing again, different coefficients are better at different sides of the graph, but there can only be one answer towards 0. Now, -1/3, -1/4, and -1/2 look very plausible, especially when you zoom in just around here, but as you can see, -1/4 is clearly the winner. But anyways, we know it's -1/4, we'll add it to this Mclaurin series, but I'll I'll make a new path where we'll keep the first 3 terms, but instead, I think I want to use 1/3 here. So, we'll compare this at the end, but yeah. Alright, this looks like a cubic, but realistically it's probably x to the 5th. Let's try x to the 5th, yeah. X to the 6th, closest function on the right side. On the left side, the closest function would either be x to the 5th, 1 coefficient, or x squared, or 1/2. But to no surprise, it's probably neither of them, which the real answer is 1/6. But given that 1/5 was actually a pretty good approximation, I will use that. And now looking at the graph we have now, clearly the purple one is our real approximation. It's a pretty good approximation, especially near 0. And if we turn on the other graphs, you can see it is just as accurate as before, near 0. But it differs around 0.5 and -0.5. So yeah, that's Mclaurin series. And I want to show you the series, the general term. So, if you were smart enough, you can probably guess the Mclaurin series pattern. Notice how even at 40 terms, let's pause at 40. Even at 40 terms, the Mclaurin series is not even not that accurate, slightly past 1. In fact, there seems to be an asymptote around 1.2 maybe. Yeah. Even at 40 terms, this Mclaurin series could not be accurate past like 1.2. Now let's try to extend this past 4, even go to 100 to really emphasize. Look at that. Even at 100 terms, it could probably get past 1.2. And look at that, you can still see the holes. Even at 100 terms, there's still a gap between them. And look at how past like 40 terms, it's just stagnant and stuck between 1.2. It will not go any more accurate past that. It really emphasizes how the Mclaurin series is truly only accurate near 0.
Hello guys, my name is ZMingQ. Welcome to my YouTube video. Make sure to like, and subscribe.